In this video, we're going to cover graphing some basic sine and cosine functions, but we're only going to look at vertical stretches and shrinks and horizontal stretches and shrinks, so we'll save the other two transformations for a different video. But before we get into actually graphing anything, we have to look at some basic terminology first. So the basic template equation we'll be looking at is y equals a times sine of b times x. So a will be responsible for vertically stretching or shrinking the graph, and the b value will be responsible for horizontally stretching or shrinking the graph. And I remember that's the case because the a value is on the outside, it's close to the y goes up and down, so that's a vertical stretch or shrink, and the b value is right next to x, and x goes left and right on the graphs. So I want to build all of this up from what we already know. So if we're looking for the domain of the sine function, the domain is where we're plugging things in, so it's these x values. And we're always taking the sine of some kind of angle. So if you think about drawing angles on the unit circle, we can go in the positive direction and we could draw some angle like that, but we could keep going. Like we could have the angle 3,600, which would just be going around the circle 10 times. And I mean, you could keep going around the circle as many times as you want. So these angles that we're plugging in for the domain, they can keep getting bigger and bigger in the positive direction, or we could go backwards and they could also keep getting bigger and bigger in the negative direction. So we can plug in any positive or negative value for the domain. So it's all real numbers. And you've probably seen that written with the all real numbers symbol, or if you use interval notation, it would be negative infinity to positive infinity. Now the range of the sine function, that's going to be the outputs over here. So that's like saying whatever value you get when you evaluate sine of some angle. So if we think about our angle that we drew here on the unit circle, the sine value is always just the opposite over the hypotenuse, which is 1 on the unit circle, so it's just the height of the triangle. So if you think about drawing lots of different triangles in the unit circle, with all these different heights here, think about what the maximum height would be. Well, if you draw an arrow straight up, so like a 90-degree angle, it's not technically a triangle, but the biggest sine value you can have would be this y value up here on the unit circle. That's the point 0, 1, so the y value is 1. And down here would be the lowest y value you could have. This is the point 0, -1, so the lowest y value, or the lowest output you could have is -1. And anywhere else on the unit circle, you can have these triangles that have all these various different heights, so you can have any y value between -1 and +1. And the easiest way to write that would be using interval notation. Since I can include -1, I'm going to use brackets, so bracket -1 to +1, and close it off because again you can include this top value. Period and amplitude are two other terms that are really important in describing sine and cosine functions, and that's because these graphs all belong to a family of functions called periodic functions. We call them periodic because they go on in both directions forever and ever and ever, and they follow this very repetitive pattern. So the period of a sine graph is how long it takes before the graph repeats. For sine and cosine functions, it's generally 2 pi. Now later when we horizontally stretch or shrink the graphs, that's going to change the period, so this will change the formula, but it always starts out as 2 pi. The amplitude is just how tall the graph is. And we always measure the amplitude as the height of the graph from the middle line. So not the entire height from the peak down to the valley, but just from the middle to the top. And if we vertically stretch or shrink the graph, that's going to change the amplitude. And it's easy to remember that because you can think A for amplitude. And the middle line is exactly what it sounds like it is. It's just the middle of the graph where it's cycling around up and down. So generally it starts out as y equals 0, and then later when we start shifting these graphs up and down, it will change. So let's graph our first parent function, y equals sine of x. And we will be dealing with these mostly in radians. So I like to start usually by counting out 12 grid lines and labeling that 2 pi. And the reason I like to do that is because if you cut that in half and you go out 6 grid lines, that would be pi. And then what's nice about this is cut into 6 pieces, so I could label this as pi over 6, and then 2 pi over 6, which would actually be pi over 3, and then 3 pi over 6, which would actually be pi over 2, and then this is 2 pi over 3, and then 5 pi over 6. And these are all nice angles that we're used to using from the unit circle. Now it'll get messy if we label every single point on the x-axis, so we don't have to label all of them. I'm just going to go halfway between pi and 2 pi, and that would be 3 pi over 2, just so we get a little bit more labeling in there. And it's also good to get a few negative labels in there as well. So now I'm just going to start thinking about what happens when I plug these angles into the sine function and see what I get for outputs. So let's start with 0 here. If I plug 0 into sine, so I'm thinking what is the sine of 0? So on the unit circle, the angle 0 would be here, and the point is 1 comma 0, and remember sine is the y value, so the value is 0. So if you plug 0 in, you get 0 out, so the first point is at the origin. So the next one would be pi over 6, and that's a small angle, so this is going to be like a short, wide triangle. The sine value is the y, or the height of the triangle, which would be 1/2. So I could plot the point pi over 6 comma 1/2. So I guess I have to label some of the y values here. I'm just going to put 1 right there. So pi over 6 comma 1/2 would be here, and then we'll just keep going with that. So pi over 3 would be the tall, skinny triangle. Again, sine is the y value, and since that's the tall side, that would be square root of 3 over 2, which is about 0.87. So I'll graph that up here pretty close to 1. And then pi over 2 is easy because that's like 90 degrees. That's just straight up here. Again, that's the point 0 comma 1. So I'm just going to take the y value, which is 1. So pi over 2 comma 1. That gets us to the maximum height of this graph. So on the left side of the unit circle here, 2 pi over 3 is, again, a tall, skinny triangle, but it's on the left side. The height is still square root of 3 over 2. So the graph will start coming down here, and it'll be at 0.87 again. And then 5 pi over 6 would be the short, wide triangle, and that height is 1/2. And now we're at pi. And sine of pi, well, pi is over here, and that's the point -1 comma 0. Sine is the y value, so we'll plot the point pi comma 0, and we'll keep going. Now, I don't even have all these angles labeled in here, and to save time, we won't actually plug all of these in. We can start to skip a few and just plug in like 3 pi over 2. So again, on the unit circle, 3 pi over 2 is down here. That's the point 0 comma -1. So I'll just take the y value of -1 and plot that here. And then thinking about 2 pi, that's 1 full time around the circle. So we're basically back at 0 degrees. That's the point 1 comma 0. So the sine value would just be 0. So you can see how the sine graph is going to go up through all these points. And it's very symmetric. So it follows the same kind of curve through the bottom of the graph. It just curves down like this and then comes back up. And it's just this wave that will just keep continuing forever. So if you follow this pattern working backwards, I know at pi over 2 it was at its maximum height. Over here at negative pi over 2, which actually, hold on, so that was 1, 2, 3 grid lines to the right. So negative pi over 2 would be 1, 2, 3 grid lines over here. So I'll label that one negative pi over 2. But over here it was at its maximum height, so this one's going to be at its minimum height. On the right side it went up, and then it came back down to the x-axis at pi. So it's going to do the same thing on the left. It will come down and then come back up to the x-axis at pi. On the right side, 3 pi over 2 was the minimum height, so on the left it'll be the opposite of that. It's going to come up to the positive 1, and then curve back down to 2 pi comma 0, or negative 2 pi comma 0. And since we've talked a little bit about even and odd functions, you should notice how this has a rotational symmetry. If I were to take the right side of this graph and rotate it 180 degrees about the origin, it would make exactly the left side of the graph. Or in other words, when you plug in these positive values, you get these outputs, and when you plug in the same negative value, you get the exact opposite output. So that makes sine an odd function. Another thing to notice is just the general shape of the graph. It goes up and then comes back down, goes to its minimum, and then comes back up. And this is where it starts to repeat again. That's where it goes through the top of its cycle again. So from 0 to 2 pi is how long it takes the graph to repeat. So 2 pi is the period. And the amplitude is 1 because from the midline to the top of the graph, it's a height of 1. So let's take a look at what happens when we start to add some different transformations in. Like number 2 here says we have y equals 3 times the sine of 2x. So having an a value of 3, that's going to multiply all the outputs or the y values by 3. So it's going to get 3 times as tall. So the amplitude of this graph is just 3. Now finding the value for the period of the graph is a little bit more counterintuitive. You'd think that by multiplying by 2, the value would increase, but multiplying by 2 is actually like increasing the speed of the graph, so it's actually going to make the period shorter. So the actual formula we use for the period is 2 pi divided by whatever the b value is. So in this case, that would be 2 pi divided by 2, which would just be pi. For example number 3, we have y equals -2 times the sine of pi over 2x. So the amplitude is just 2. I know we said before that the amplitude is the a value and we have a -2 here, but the negative is just going to flip it upside down, and the amplitude is more of like a height or a distance measurement, so we just say that the amplitude is just +2. Now it's kind of weird that the b value has a pi in it, but that's just going to make the period like a whole number value, so let's see what happens. We said it was 2 pi divided by b to figure out the period, so we'll say 2 pi divided by pi over 2, and dividing by a fraction is like multiplying by the reciprocal, so I'll think of this as 2 pi times the reciprocal, which would be 2 over pi. And multiplying fractions, you just multiply straight across, so I'll just put that over 1. and then on top we'd have 2 pi times 2, but actually wait, I'm going to cancel the pi's first. So we'd have 2 times 2 on top, which would just be 4, over 1, so we just get 4. So this function is going to repeat the pattern every pi units, or about 3.14. This function would take 4 units until it starts repeating its pattern. Alright, so now let's take a look at graphing these. We just looked at this function, and we said that the period was just pi, and the amplitude is 3. I'm going to hold off on answering the range until we've graphed it, and we can come back and look at the graph and just see what the range is. Knowing that the amplitude is 3 means that I'm going to number the y-axis so that we can reach that height. So every grid line is just 1 unit. And for this graph, I'm going to do the same thing I did before. I'm going to go out 12 grid lines and label that 2 pi. And again, the reason I do that is because taking 2 pi and dividing it into twelfths gives us values that we're used to seeing from the unit circle. So I'll start just like before, like thinking about plugging 0 in. Well, 2 times 0 is still 0, and the sine of 0, as we saw before, was 0. 3 times that is still 0. So plugging 0 in, we still get 0. That means we still start at the origin. So that's kind of a hallmark feature of sine, is that its starting point is at the origin. And you'll see in a little bit, cosine does not start at the origin. But after this, the way I'm going to graph this is knowing that the period is pi tells me that it's going to repeat. If I go out pi units, it's going to be in the same exact position. So that means that this graph has to go up, come down, go down, and then come back up in that time. So it's going to look kind of like what I just sketched, except for remember the height or the amplitude was 3. So it'll need to be a little bit taller. But notice how from 0 to pi gets me through the full graph, and right in the middle it's going to hit the midline again. So I'm actually going to put a point there, and then just knowing that right in between these 2 points, that's where it has to hit its maximum. So this would technically be pi over 4. So I'll go from pi over 4 up to its maximum height, which was 3, and that's, again, from the amplitude. So I just know I have to go from the origin up to this point, and then back down, and then I'm going to continue that same pattern going down. So right between pi over 2 and pi, I guess that would be 3 pi over 4. I'll hit the minimum height, which is at -3, so I'll go all the way down, and then come back up. So when you're graphing these functions, you really just need these 5 key points, which come from the equilibrium points, which are like right in the middle, and then the max and the min height. And once you've graphed one period, you can just keep that pattern going. So it's like every 1.5 grid spaces, I'm putting a new point. So I'm going to go right between pi and 3 pi over 2, and this graph is going up now, so I'll put its maximum height there, and then a point at 3 pi over 2, comma 0, and then down here at its minimum height, right between these two, and then back to the equilibrium point at 2 pi. So then just continue the pattern going to the left as well. So the range is just all the y values, and you can see that it's going from +3 all the way down to -3. I'm going to write that using interval notation, so I'll go from -3 to +3, and we're including those values, right? Like there are points up there and down here, so we'll put brackets around these. So for this example, we said that the period was 4 and the amplitude was 2. So when I'm labeling this graph, I'll count up 2 grid lines and label that 2 and then -2 down here. But since the period is a whole number, I'm not going to label the x-axis with like pi type numbers. I'm just going to count out those same 12 grid lines and put 4 there. So when we're graphing these, we like to take half of the period and label that. So 6 grid lines out would be 2, and 3 grid lines out would be 1. Labeling the graph this way also helps to keep it nice and spread out so it's not crammed in one little area. So now I'll start graphing this. Remember when we plug in 0, sine of 0 is 0, times -2 is still 0. So I'll put the point at the origin, and remembering that the period is 4 tells me that if I go out 4 units, that's where it's going to repeat. So I'll put another point there at 0. And remember with these sine graphs that the beginning point and the end point kind of mark the whole period, but right in the middle there's another one of those equilibrium points. So right in the middle of 0 and 4, there's another equilibrium point. Now this graph is different because the a value is negative. So instead of the graph going up first, like here from the origin we went up, instead of doing that, this graph is going to go down first. So right between 0 and 2, it's going to hit its minimum point, which is at -2 since the amplitude is 2. So you can see how it's going to dip down through its minimum point and then come back up to the equilibrium at 2. And then I've got to go up and then come back down for 4. But I've got to get all the way up to the maximum of the amplitude, which is +2. So we'll go through that point and then down. So that makes up those 5 main critical points that we have to graph, the 3 equilibrium points and the max and the min. Then I'll just continue that pattern going to the left. So the range of this graph goes from -2 all the way to +2. So we'll say bracket, -2, comma, +2. So now we have an example where we just have to think backwards because we're already given the graph and we have to come up with what the equation is. So I notice that the graph starts at 0, 0, so that makes me think it's like a sine function. And it's going up and then back down, and then it starts to repeat here at 4 pi comma 0. So remember we said that the period was 2 pi divided by b, but in this problem the period is 4 pi. So here I have a little equation and I can solve this for b. And you might have seen before this little trick we talked about where you can just, in this type of equation, you can switch out the b and the 4 pi on the other side, which is kind of just a shortcut that saves us some time, because then we can cancel the pi's and 2 over 4 simplifies to 1/2. So the b value in our equation is going to be 1/2. So I know it's sine and it's going to be 1/2 x, but I have to figure out what the a value would be. And I see that the maximum height is 4.5, and then down here it gets to negative 4.5. So the amplitude must be 4.5. And I'm going to go with positive because from the origin, like its starting point, it's going up first, so that's a positive sine graph. If you feel like filling this information in, it's all the same exact stuff from sine. The one main difference between sine and cosine is where they start. And that's because if you think about on your unit circle, if you start with the angle 0, remember that's the point 1 comma 0, sine was starting with this y value of 0, but cosine, the x value, actually starts with this value 1. So when you plug 0 in for your first value, you actually get an output of 1. So to label the graph, I'll just put 1 up there and negative 1 down here just to keep it spread out a little bit. And just like before, so the period is 2 pi, I'll go out 12 grid lines and label that 2 pi. And then fill in the rest of the x-axis labels just like we did in the first graph. So this one starts at 0, 1, and again the period is 2 pi, so out here at 2 pi I'm going to put the same point up at 1. And this one isn't labeled as detailed as the first graph was, but let's just see what happens when we plug these points in. So pi over 2 is right here, and that point is 0, 1, so the cosine value is x, that's 0. So at pi over 2, cosine value is 0. And if you go to pi, that's over here, and that's the point negative 1, 0. So the cosine value is negative 1. So that puts the point down here. And then 3 pi over 2 is going straight down. That point is 0, negative 1. So the cosine value is 0. So you can start to see the wave pattern is going to dip down and then come back up and reach its max height again, and then just keep going. And then just follow that same pattern going to the left. So it's got to come back down. So I'll put this point at 0. And then negative 1, back to 0, back to positive 1. So with cosine, you can see it doesn't have rotational symmetry like the sine function does. This actually has reflectional symmetry. It reflects over the y-axis. It's exactly the same on the left and the right side. And that makes this an even function. These next two examples have the same transformations as the first two examples did. It's just a typo that says sine instead of cosine. But the transformations affect the graph exactly the same way. So the amplitude is still 3, and the period would still be pi, just like it was before. And then over here, the amplitude is 2. Remember, we ignore the negative, and the period was 4. So remember, the only difference between sine and cosine is just that starting point. Sine starts at 0, cosine starts at 1. So let's graph our last example here. It's y equals 2 times the cosine of 4x. Again, that's a little typo there. So the amplitude is 2. And to figure out the period, we'll just take this b value, and we'll say 2 pi divided by b, so 2 pi divided by 4. And so we can simplify that down to just pi over 2. Now that means that the graph is going to repeat every pi over 2. And that's kind of a small value. That's just 90 degrees. That's kind of a small portion of the unit circle. And I don't want the graph to be like super tight like this. I want to be able to see a lot of it kind of in detail. So I'm going to do the same thing I did before, except for I'm going to put pi over 2 out at 12 grid lines. So that'll spread it out a bit. It'll take up more of the graph. And now I just have to think, okay, half of pi over 2 would be pi over 4. So I put that here halfway out, so that's 6 grid lines. And then half of pi over 4 would be pi over 8. So if I just go 3 grid lines out, that would be pi over 8. So this is 1 pi over 8, and then 2 pi over 8, which is pi over 4. So then this would be 3 pi over 8. And then one more section of these 3 grid lines, that would be 4 pi over 8, which would simplify to pi over 2. So we're good. Now this might be a little intimidating at first because we're not used to plugging in pi over 8. Like that's not a special triangle angle. But that doesn't matter because as long as we remember the shape of cosine, it'll be fine. We remember that cosine starts at its maximum height, which before I was saying that was 1, but this has an amplitude of 2. So I'm going to put a 2 up here and negative 2 down here, and its first point will be at 0, 2. So it always starts at its maximum height. And then it repeats out here after its period of pi over 2, it's going to have the same maximum point again. Okay, now the general shape of this is it's got to dip down in the middle and then come back up. So I know right between here and here, I've got to have its minimum point, which is at negative 2. So pi over 4 comma negative 2, and then right in the middle of the maximum and the minimum points, we have the equilibrium point. So just recognizing the shape, that it goes from its maximum to the equilibrium to the minimum to the equilibrium back to the maximum again, helps you graph the function really fast. You don't have to worry about plugging things in point by point. Keeping that pattern going to the left, it would have to hit its equilibrium point, and then its minimum point here at negative pi over 4, and then back to equilibrium, and then back to its maximum point. Again, with the range, it's going up to its maximum, the amplitude is 2, and then all the way down to its minimum, which is negative 2. So I'll write that as bracket negative 2 comma 2.